All right, sports stats students, we are beginning our next section, and that is going to be this unit here. What we're probably going to do after we finish this content is we will be taking a test over really all three of these sections that we've covered, basically with the probability, normal distribution that we finished up, and then what we're going to learn here with all the sports betting ideas, as well as just sports strategy and different things like that within this. So I may or may not do this last highlighted part. We'll see. But we can definitely spend a lot of time in this section and talk about probabilities that are used within creating odds and things like that for sports betting. Okay. Before we even come close to talking about that, we need to go ahead and go to our notebooks, and we want to start. We're going to title this random variables, because that's what these are. And that's sort of going to be our foundation for understanding a lot of like the sports betting ideas and things like that that we'll discuss. So we're going to write the definition of a random variable. By the way, you should start probably a new page for this, but let's go ahead and get a definition. A random variable takes on numerical values that describe outcomes of a chance process. Okay. So I want to go ahead and pull in an example that we've seen before. I'm going to put two examples up on the screen. Okay. So we have two probability distributions. So let's also remind ourselves of what that is. So we can write this down. What is a probability distribution? A probability distribution lists the possible values of a random variable, how likely they are to occur. Okay. Now, we have two different probability distributions here. This one is one that maybe we recognize from our baseball season. We had the outcomes and their probabilities associated with them. Okay. And then down here, we have a new context that we've not seen before. I haven't even described this, but one of these is a random variable and one of them is not. They're both probability distributions, but the key here is this, and you can underline this in your notes. It's that it takes on numerical values. So notice how this goes from 4 to 5 to 6 to 7, whereas this is just counting or just stating what happened. So out, walk, single, double, triple, home run. So that's all we see with this top distribution. Okay. So we're going to go ahead and start with this. So just to give you some context, this is the data. So what we have here is, and we'll write this. So this is our example. You can go ahead and write this. So example, let me make sure I have this right. This is the number of games required in a World Series. We'll make sure we specify this as MLB. So this is baseball is what we're talking about. So this is MLB World Series from we have 1945 to 2010. So if we need to do this, if we need to pause We can do that. Let's write this example in this name here, and then copy this table. Very simple version of this table in your notes. And we'll go ahead and start analyzing this. So this is a random variable. So we'll say random variable. 1, it's numbers. X is numerical. And 2, you have the probabilities. Now, these probabilities that we see here, what this is showing is that there's 65 World Series that have been played on this in this data. So these are all experimental probabilities, essentially. Okay, so and we talk about in sports, like everything's an experimental probability. There's no way that we say, oh, what's the odds that they're going to play a 6-game series? Well, you can't just look at 2 teams and just know that for sure. But you can get an estimate of what's happened in the past. It's kind of like with March Madness, when we made our power models, that's what they're really using. They're using data from old. Now, you could argue that the game has changed a little bit for both of the sports. What is representative of teams from the 1940s, even through like the 70s, is probably not applicable to today's game because things change all the time in sports. But this still is one of our best guesses. Okay. And so that's sort of the intro to the idea of random variables. Now, the reason that this is important is because we're going to learn how to calculate a very important idea. We have what's called the expected value. Okay. Let's actually put a little star beside that. This is probably one of the most important ideas that, in my opinion, probably one of the most important ideas to take away from this class. We're going to kind of go outside of the of sports for part of this. We're going to look at life insurance with this, and we're going to look at lottery as well, and talk through examples in there. But we'll start here with this baseball example. And so we're interested in the expected value. Now, the expected value is, I'd say it's a synonym for the mean. Okay. So the expected value mean of a random variable. Okay. We're going to learn how to find the expected value for this. So what is the mean of this distribution? Well, if we wanted to just add these up, like if I just said, hey guys, find the mean of this, you would take 4 plus 5 plus 6 plus 7. Okay, that's 22 divided by 4, and you get 5.5. But that's actually not the best way to do this, because you'll notice that 7 is worth more than all the rest of these. I don't know if you noticed that, but we kind of need to create a weighted mean for this. So that's going to bring us to a new formula that we're going to introduce. And let's start with a definition. The expected value input there, of a random variable is equal to the average value of the random variable if the chance process were repeated many times. Okay, so there's our definition for a random variable. Here we go. We do get a formula for this. So our formula, I'm going to skip ahead to where I've typed it out because I got to do a bunch of math typing. I'll insert this first part though. So the first symbol that we're going to introduce is one that we introduced for the normal distribution. So we have mu, but now we're going to give it a subscript of x. Okay. And really what that's doing, it's just telling us, so we know that we're talking about this variable x that we see here. So mu of x is talking about that. So that's what that x is. Okay. So it's just helping us identify in case we had multiple variables that we were looking at. So that's all that that's there for. Another way that you might see this in a problem might be capital E parentheses x. That's another way that you could see it. But now I'm going to actually put like a sort of a crazy looking formula in here. So I'm just going to skip ahead to that. Okay, so here it is. So we've seen this symbol before. This is the capital version of sigma. And what it actually means is, you can redraw this if you want to. What it means is to sum. Let's talk about what this is, and I'm going to copy this back down here so that we can see this a little bit better. So you don't have to rewrite this or anything. But what this is telling us to do, it's saying right here, we're going to take the x value and we're going to multiply it times its probability. So for my example here, so example, World Series. So you can write this. What we're going to do is we're going to take 4 times, let me actually make an equation. So we have 4 times its probability, 0.185. Okay. And then we're doing that for all of them. Okay. So I would just repeat that. But what the sigma is actually telling us to do is telling us to add up. So it's 4 times 0.185. And then we add that to 5 times its probability, 0.185, plus 6 times 0.215, plus, and then we take 7 times 0.415. Okay. So this is going to get us our true expected value. When we just added the 4, 5, 6, and 7 divided by 4, we got 5.5, but this should be more representative. So we can pull up Desmos, and we can type all of this in to our scientific calculator. So I should be able to just copy and paste this, I hope. Let's see about that. Formatting here. Okay, so it's actually, okay, so I have it over here. It's actually 5.86 is what it ended up being. So it's just a little bit different than that. Well, this will almost always be wrong, especially if the probabilities are way different. Like if this was 0.9, it would really be off by quite a lot. Okay. So that's why we have to sort of get this weighted average. So we'll put this in our notes here, 5.86. Okay. And so then we want to interpret what this actually means. So we're going to use we'll use this symbol here. So mu of x equals 5.86. So let's interpret that. This value indicates that if we were to randomly select World Series over and over, average number of games in the selected series, be about 5.86. Okay. So it's a pretty simple example here, but this is at least a pretty good estimate of what to expect in a World Series game for particular outcomes. So I'm going to have you guys try this again. I'm going to get another context, and I want you guys to just calculate the expected value for another scenario. So the Masters is coming up soon. Maybe there's a couple people who are golf enjoyers, but now we're going to do a golf example. This is called Birdies in the Azaleas. When is the Masters? The Masters is pretty soon. I think it's this coming weekend or the next one. But hole 13, it's 18 holes for golf, by the way. For those that are non-golfers, you play 18 holes. The 13th hole at Augusta National Golf Course, this is in Georgia, by the way, is one of the most famous holes in golf. It's lined with the course's signature azaleas. I don't know if you can see them in the picture here. This hole is also a favorite of players for its relative ease. The hole is a par 5, meaning that professional golfers would be expected to complete the hole in 5 strokes. X, here's our random variable. X is the score on the hole 13 for a randomly selected golfer on day 1 of the 2011 Masters. The probability distribution is shown below here. Okay, so this is a random variable because this is all numbers. And so this only works if it's numbers. So this is the number of strokes it took. Now, 1 under, or 5 would be par, 4 would be birdie, because it's 1 under, and then 2 under would be an eagle. So you can see the most likely thing to happen for the pros is par or even birdie. They're both very likely. Okay. But we want to go ahead and calculate the average for these. So I'm going to have you guys do that. You're going to calculate average for this scenario. So you can pause the video and give everybody a moment to do that. Okay, so what you should have done, and we'll put this in Desmos, is 3 multiplied. I'm just going to use parentheses now. 0.04 plus 4 times 0.414 plus 5 times its probability 0.467 6 times 0.051 plus 7 0.03. Okay, so we have that, and I want to go ahead and put that into Desmos. Hopefully it just computes for me without any issues. Perfect. So 4.627 is the expected value. Okay, so that is what is expected to happen on this hole. Okay, and let's interpret. And this is what we're going to say. If we were to randomly select golfers and over day 1 of the 2011 Masters, their average score on hole number 13 would be about 4.627. Okay. Cool. So these are pretty straightforward. In a test question, I would ask you to find the expected value for that. And then you pick the correct answer. So that's pretty straightforward. Okay, so this next example that we're going to look at is not sports related. It's actually lottery related. This is, in fact, not like a resource from like a educational resource or anything like that. This is like legit Michigan Lottery official YouTube video. Okay, and what we're going to be learning or like seeing in here is the game called Keno. So in our notes, let's do example Keno. Okay. Now, what we're going to unravel within this is what is the expected amount that you will win if you play this game. And that's where this expected value really comes in handy. It's not just for money related things or these ideas here. It can help with strategy as well, which we'll talk about that in a little bit. But but with the expected value, it's what we expect to happen if the process were repeated many, many times. So if you were to play this game many, many times, what would be your expected amount that you would win? Okay, so we're just going to watch the video, and I'll hide my screen. So we'll just watch this video. Just realized my desktop audio is not working. Give me one moment. All right, we are ready. Let's watch this.
Are you ready for Michigan Lottery's action-packed Keno? The daily game where you can win up to $250,000.
Welcome to the show. I'm your host, Bob Buxley, and I'm not wearing any socks. Let's welcome our contestant, Cynthia, to the show. It's Keno. Match 10 of 22 numbers drawn and win the jackpot. You can even win without matching any number. That's a lot of numbers to choose from, Cynthia. Let's play. What do we do again, Larry?
Choose your numbers. First, you'll select 10 numbers from 1 to 80. We'll draw 22 numbers. If yours match, you could win. And for you players at home, select your 10 numbers using a play slip. Or forget the play slip and ask your retailer for an easy pick. And remember, Bob, one play will cost just $1.
No way! Just $1?
Yes way, Bob. $1.
It sounds like fun, Bob.
More fun than a barrel of nachos, Cynthia. Well, okay then. Let's play Keno. Well, alrighty then. It's time to choose your numbers.
I pick 5, 11, 22, 27, 33, 38, 44, 56, 61, and 66.
Remember, drawings are held 7 nights a week. Okay, Cynthia, let's see if you've won.
Oh, well. Better luck next time.
It's not over yet, Cynthia. In Keno, we draw more numbers than you pick. 12 more to go. We have a winner, Bob. Cynthia has matched 8 numbers.
Ha! You are number one. You are number one. Ha!
For you folks playing at home, download the Michigan Lottery mobile app or visit MichiganLottery.com to see if you've won. To claim prizes of up to $600, take your winning ticket to any Michigan Lottery retailer. For prizes over $600, visit any Michigan Lottery office or licensed claim center.
Say, Lair, is that where that money tree is growing?
Yeah, Bob.
Thanks for playing Michigan Lottery's Keno.
This game demo does not reflect actual odds. Must be 18 or older to play.
All right, so this is exactly what the screen that we want to look at so that we can tell how we're going to do playing the game. Okay, so I am going to, well, I'll just keep this. Actually, I'm going to go ahead and snip this just so we have it. So odds of winning. Okay. So what I would like everybody to do is open up a blank Excel sheet. So let's do that. Blank workbook. And what we're going to do is we are going to create our probability model for this random variable here. Okay. And then we'll transfer this into our notes as well, but we're going to start with this. So we have X and we have probability of X. Okay. And so X, I'm going to merge some cells. You don't have to do this, but I'm just doing it so that you can see what this is. So X is equal to the amount won playing Keno. This is specifically Michigan State, the state of Michigan's little Keno. Obviously, we live with Tennessee Lottery. So this is similar to theirs. But let's go ahead and list out the amounts that we could win playing this game from the least to the greatest amount. And you do want to think this way. What's the least amount you could make? Well, as you're looking at this, you're probably looking at my screen and you say, oh, well, it would be a free $1 instant ticket. But did you really win anything if that's what happened? So how much does it cost to play? Well, in the video, they said it costs $1. So if I paid $1, I get back $1 if this happens. Okay. But that's not even the lowest amount that we could win. And maybe you're not even thinking like this, but we paid $1 to play, right? If we don't win, guess how much we gained? We gained -$1. So in our first cell, we're going to put -1. Okay, and if you, we'll leave it like that. So -1. X is the dollar amount won playing Keno. Okay, so -1. Then we win a free instant ticket, but we didn't gain $1. We gained $0. All right. Hopefully that makes sense. What's the next amount though? Okay, so you could win $7, but it's not actually $7. You paid $1 to play, so it's $6 that you actually won. Okay, and then it's all of these other amounts. So 25 is actually 24. 250 is 249. Adjust these. I guess I can make this wider. 249. 2,500 is going to be, so this will actually be 2,499. And then the biggest prize is this 250K. So 2,49999. There we go. Okay. So there it is. So these are all the dollar amounts that you could win playing this game. So that seems pretty good, right? Until you look at the odds, and it's really cool that they show the odds. I think maybe they legally have to in Michigan. I don't think Tennessee has to show their odds. I'm not really sure. But we're going to go ahead and type these in. Now, you'll notice that we don't know what this is yet. So you can go ahead and put a question mark in there. We'll figure that out in a second. We do know the odds of winning for winning a ticket back is 1 in 32. Now, hold on. I'm going to pause as well. Some of you might be saying, well, the overall odds is 1 in 19. So wouldn't that mean it's 18 out of 19 to lose the $1? Yeah, but I want to get it more exact. This is written this way for TV because they don't want to put the actual probability, which is probably a crazy fraction or a decimal. So we'll start in here, and you guys can actually just type the actual decimal in here, equals 1 divided by 32, and it will give us it'll change it from a fraction to a decimal. We actually prefer that, okay? In this next one, the probability of winning $7 is 1 in 52. So 1 equals 1 divided by 52. Go to column E here, $24, that's winning. $25, that's 1, so equals 1 divided by 313. Okay. And then we can extend this over to show more decimal places. We're going to need that, especially for these larger values. So in this one, right here, 249, that's equals 1 divided by 3115. There's that. You can see that's a little bit lower. The next one, 2,500 is 1 divided by 57,070. That's giving us a scientific notation. Let's see if we can mess with this to make it. I guess it is just going to keep it in scientific. Let's see if we can just do a number. How many decimal places do we have to go? Okay, so if you change we messed around with this yesterday with the NBA normal distribution heights. Change it to number and then move the decimal point with that button there. Shrink this a little bit. There. Okay, because we know we're going to need a lot of space for this one. So I'm going to go ahead and extend that because the grand prize is equal to 1 divided by 2,546,203. All right, so yes, let's change it to a number, and then let's move the decimal point. There we go. Okay. So we are going to find this because we know that all of this should add up to 100. Okay. But if we just highlight this, we see the sum at the bottom. Let's go ahead and in here, let's get our formula. Instead of this question mark, you can delete that and hit it equals. We're going to do 1 minus the sum of all of these cells. Try that again. Equals 1 minus the sum of all these cells here. What's happening here? Might be better to do it this way. Maybe you're getting yours. I'm just going to put the sum down here. That is all of them added together. I'm just going to do 1 minus that. That seems more efficient. There we go. Okay, so this is the probability of losing, which, by the way, 18 divided by 19 is pretty close to it. Small places here. Okay, pretty close to it, but they wrote 1 and 19 here just to make it a little bit easier. Okay, so we have all of that. Now what we're going to do is, and I'm going to move this down here. Okay. Now what we're going to do is we want to find the expected value, but I'm going to have, I'm going to add borders to this. What I want everybody to do is make a sketch of this in your notes. Okay. So you've got it on your screen, but let's pause this video, give everybody a moment to write this down in their notes. I'm going to go ahead and show, like, this is what it should look like in your notes. So now we want the expected value in here. If you haven't paused it yet, for everybody, right, make sure they got this written down. That's fine. We're going to find this expected value. Okay, instead of us typing this one at a time, we already know that we have Excel that can help us with this type of problem. Okay. So what we're going to do, I'm actually going to move all this down. I would recommend that you guys do the same thing. We're going to make a column down here called X star PX. Okay. Or a row. And what we want this to be is these being multiplied together. Okay. That is, in fact, the formula that we wrote down right here. Okay. So it's this part of it. We just want to multiply each value by its probability. So what we're going to do is we're going to click on the value amount times its probability, hit enter. Then we repeat that here, but we know that we can just drag this over. Okay. So this represents all of those that got multiplied together. Obviously 0 times anything is 0, but it's all these being multiplied are going down here. So that's saving us having to like type it in. You also don't have to worry about like writing this on your notes. We don't need to worry about that. Okay. No worries. No worries. Okay. So next, let's add these up because that is what we want. So we're going to do EX, that's expected value, and that's going to go right here. So it's the sum of all of these. There we go. That's what we want. Right there. And we're going to round this and we're going to put $1 in front of it. And we'll round it to the nearest cent. This is what's happening in this situation. For every dollar you put in, you're expected to lose 53 cents for every single dollar that you put in. Okay. Now that may not happen. You could win. Could win the big prize amount, but this, by the way, is not experimental. This is theoretical. Like they know that this is actually what's true. And as a matter of fact, if you did win, they'd probably be very happy about it because it would encourage more people to play so that they could fall prone to the law of large numbers that's happening here. Okay, let's interpret this. if we were to play Keno many times, we expect to win on average negative 53 cents. Does that make sense? So that is a very practical application of expected value. And trust me, the people that made this video, made this game, they know expected value. And that's exactly what they used to put this game in their favor. I would say it's pretty likely that most lotteries are going to be in this ballpark of a negative number. And it's pretty set. It's not like sports betting where there's a lot of variability that happens, a lot of uncertainty. We'll certainly have a lesson about that in the near future, as I've promised. But this is showing you like how casinos even work. Like if you go and play a slot machine, there's an expected value for it. There's no accidents there. They're not in it to make you any money. They're going to get their money long run. So if you played this game thousands and thousands of times, yeah, you may win once, but at the moment that you win this, you've already put in so many dollars that it kind of negates it. You're going to lose 95% of the time. And I'm sure that there's a reason they don't put that in their promo saying, oh, the odds you lose is 95%. Okay. So I think I'm going to stop the lesson there with that one. There will obviously be some assignments that are forthcoming within all of these skills, but you guys can work on yesterday's assignment. It looked like only one person had turned it in. I am expecting to have my child on during probably the early morning on Thursday. I don't expect I'm going to be able to get back to most of my emails until maybe Friday at best. Okay, I do want you to email me. I got several emails from people about assignments. So you can send the emails. I'll just kind of be slow to get back on those. But hopefully you enjoyed that little lesson and learned some things right there about expected value. And you're going to play baseball Friday, and then we'll have more lessons on this next week on Tuesday because Monday's the eclipse day. Have a good one.